All the structures that we see around us could not survive because of the tremendous densities and temperature. Not even the ordinary material that we're made of, atoms and molecules, existed then. Any human being would have been crushed and out of existence.
Can you imagine the beginning of everything? The moment when matter began, when particles and atoms were formed, and when time itself was set in motion. This moment, scientists now call the Big Bang. To begin to understand this event, you might turn to the world's largest and most powerful supercomputers. You might, unless your name was Emma King.
It's kind of an age-old question, you know, right from the dawn of time, people have looked up into the night sky and thought, you know, what's out there? Are there other, you know, are there aliens out there? What is it? What's the universe made of? What's in it?
Final year PhD student at Nottingham University, Emma King has embarked on a project that will take her not only to the limits of modern mathematics, but right back to the start of the universe.
Astronomy is a funny science. Unlike most sciences where you have a laboratory and you can go into your laboratory and you can set up an experiment and test things, in astronomy you can't go to a star, you can't collect a bit of it to see what it's made of. When the universe formed, it's full of large clouds of gas, and these clouds of gas collapse under their own gravity to form galaxies and stars. And there may have been large-scale magnetic fields inside those clouds, and when the clouds collapse under gravity, the cloud affects the magnetic field, and the magnetic field affects the cloud. And so I've been looking at the interrelation between those two things.
Magnetism is so complex, it is generally left out of models of the universe. But for Emma, the complexity of magnetism proved to be the attraction. Professor Peter Coles is Emma's supervisor here at Nottingham. Even before they first met, he was aware he had a very special student on his hands.
The first impression one gets of a PhD applicant is the paperwork. And we were really blown away by the paperwork that came with Emma because she had stunningly high marks. One of her references mentioned the fact that her answers to some of her exam questions, written under exam conditions, under great pressure, were actually better than the model answers that the examiners had provided. So we really didn't know what to expect when she turned up.
The budding mathematician that finally did turn up went way beyond their expectations.
I had a sword fighting lesson every week. I play the harp. I go live role-playing at least one weekend a month. I do some fire breathing and some fire sword stuff for displays. I currently have one unusual pet, and that's my snake. That's all that springs to mind at the moment. There's bound to be other things.
These distractions help Emma concentrate and find the inspiration she needs for her work.
The work that I do is largely looking at the very first few seconds of the universe, what's called the early universe. And it's a place that's very hot, very dense. We have to assume that the laws of physics that we know about now still apply then. That's actually the reason that you can't get back right to the very beginning of the universe, is when the universe gets too dense, it becomes what's called a singularity, and the laws of physics break down there. So we actually don't know what happens right at the instant at the beginning. But assuming that the laws of physics have stayed more or less the same throughout the history of the universe, we can theorise about what happened in the first few seconds and minutes after that.
It's a bit like a crime scene investigation that, you know, if a bomb goes off somewhere, you can't really go back and understand and visit the actual explosion. But by looking at what happened and where things went and what fallout occurred after this explosion, you can actually figure out, usually, exactly where it happened, how hot it was, what kind of material was involved, and so on.
With no physical evidence available from 14 billion years ago, Emma needs to imagine a simplified universe.
Basically, the only way we can do it is by creating theoretical mathematical models that describe the universe in that very early state. And we use those to make predictions. And then you look at the universe around us and you compare the real world to this model that you've made. And hopefully the two coincide, and if they don't, then you've got it all wrong and you need to go and do it again.
In Emma's case, these models take on the form of complex equations, and the modern world of physics generally relies on computers to solve them. But Emma is something of an unusual cosmologist.
She doesn't like using computers. She, I would say, is competent at doing that, but she doesn't enjoy doing it. She realizes that it's necessary in many cases, but that's not what drew her into the subject, not by any means.
But there's a good reason Emma has a problem programming computers.
I was diagnosed as being dyslexic when I was very young. I was clearly, in some ways, perfectly intelligent, and yet so unable to grasp what seemed to other people to be very simple concepts. I find it frustrating. I find it very difficult to go through that process to make sure it all works. So I try not to use the computer unless I absolutely have to.
Dyslexia can take on many different forms. For Emma, it's numbers. Despite this, she has gone on to become an award-winning mathematician. The reason is that there's a difference between simple arithmetic and complex mathematics. And Pete, her tutor, has devised a test to demonstrate this.
So what are we doing here?
Well, we're going to try some mathematics, just to find out what you can do.
Lucky me.
So we'll start off with some simple things.
What is 12 times 13? You have to be kidding. On a day-to-day basis, I'm sure my dyslexia affects my work. I'm quite used to coping with it, and so I've developed a lot of strategies to minimise its impact. I make notes about absolutely everything. I don't do any work without a pencil and paper because I simply can't hold things in my head to work with them. Is that right?
That's right, yes.
Yay!
What about this one? Yeah, algebra might help you here.
Yeah, so it's 100 plus 1 times 100.
She, curiously, I think, finds it easier to work algebraically with symbols rather than with actual numbers. That's kind of strange to think of. Most of us learn to do arithmetic before we do more higher level mathematics, and are more comfortable with arithmetic than with higher level mathematics. But Emma's the other way around.
Numbers just don't make any sense. I look at them and they don't seem to mean anything. Addition, I tend to be better at. Mathematics and arithmetic are two different things which a lot of people get confused. You do use arithmetic when you're doing maths, but to me arithmetic is the thing with the numbers. It's the addition, subtraction, multiplication with numbers that you learn to do when you're very young. Maths is this sort of thing. It's the symbols and the letters and the manipulation of those. Basically algebra is more what I think of. Algebra and calculus are the sort of things that I think of as maths. But most people see the two as more interrelated than I find them to be, and consequently they find it very surprising that I can be so bad at arithmetic and yet perfectly good at maths. A double dot minus. A dot is d by dt of t to the p. A dot squared is a pi g. If I differentiate the second one, I get the first one. A is a function of time, 2p minus 2, or pi g over 3 rho a. 2/3, so A is proportional to t to the 2/3. Done it!
That's the Einstein de Sitter universe.
Yes, which is much easier.
Congratulations.
Thank you.
Emma may not be able to do simple sums, but in a few short moments she has reduced complex mathematics down to an equation that describes the mechanics of a simple universe. After a hard day solving the riddles of the universe, Emma needs to find ways to relax. But it seems ordinary distractions simply aren't enough.
Reptiles are absolutely fascinating, I think. I just find everything about them amazing. The snake only needs to be fed once a week. The way that their bodies work, they are so different from mammals. I think probably the biggest thing is that I'm easily bored. This is one of the reasons why I do so many different things outside of the physics. You get stuck in a rut, and I can't get out of that unless I go and do something completely different for a while.
And for things to do outside of work, you don't get more different than live role play.
I do like living in sort of an imaginary world in my head, if you like, and this is sort of the ultimate version of that. I actually get to really be in my imaginary world.
Shall we leave before any more of them turn up? That would be a good plan.
You need imagination to get ideas for where to go next in the work. You don't sort of, when you're learning science at school, it always seems like you're following this kind of set path. But that's because other people have explored before you and sort of shown you the route, and so you go down the well-trodden path because you know that's what gets you to where you want to go. But when you're doing research, you need to have ideas about which direction to go in and how to go about getting where you're trying to get to. So it's all, you need sort of creative ideas quite a lot.
When Emma was at school, she was the only girl in her class who wanted to study physics. Years later, she's found her way back into the classroom. Only now, she's not the only female with an interest in the subject.
The universe starts off exploding. Somehow we end up here with stars and galaxies and planets. Anybody have any idea what happens in the intervening billions of years? One of the things I'm involved with is a project where I go into a local school and talk to the students there, and I do all sorts of different things, talking to them about science, about being a scientist, helping out teaching lessons, all that sort of thing, because it's important to communicate science in a friendly and approachable way to children. There is basically no answer to any of these questions. You can't ask the question what happened before the Big Bang, because time was created at the Big Bang. So the question is essentially meaningless. There was no before because there was no time before. Science changes every year. Every year we discover something new about the universe. Every year our models of how it works change. And I think it would be a great shame not to move those into schools, because I think a lot of them are very exciting new ideas and they get children excited and they get them wanting to learn more about these things.
All academics in science realise that grassroots kind of interest in science is really essential to what we do, otherwise the subject will die out. But very few actually make the effort to go into schools and try and make their work accessible to ordinary people, non-specialists. But Emma certainly puts a lot of her activity into that.
It's this ability to communicate and pass on her love of science that holds the key to Emma's future.
It's tragic that people don't get the enjoyment that I get and the fascination that I get and the sense of wonder that I get when I learn about the universe and the way it works. I just want to share that with people. I want other people to get this fabulous sense of how amazing the world is that I get.
Emma's passion for knowledge is unstoppable, and she's already planning her next project.
I'm using general relativity to look at a hypothetical universe which has a very large-scale magnetic field that permeates the entire universe, and just having a look at the maths of that and seeing if anything interesting crops up. And I don't yet know whether it will or not. We shall wait and see.